Hello and welcome to part 3 of Physics Paper 1 Edexcel 2018 series. So let's start straight away. So a student sets up the apparatus shown in figure 9. Spring, iron nail, wires to power supply and solenoid. So solenoid just could be coil of wire. Okay, around sort of twisted around a tube. It could be twisted around things. So just coil of wire is the solenoid there. So when the current in the solenoid is switched on, the solenoid attracts the iron nail above it. Describe how the student could use this apparatus to investigate how the size of the current in the solenoid affects the force of attraction between the solenoid and the iron nail. Okay, so obviously it's attracted to this pointer. Okay, so what we need to do first of all, okay, is note where that pointer is. It's not 0, is it? It's already hanging at a certain point. So the first thing to do, okay, is note the position of the pointer before the current is switched on. Before the current is switched on. Okay, so we need to know what it was before we can measure a change, don't we? Okay, so turn current on. Turn on current and use ammeter to measure the current. So you want an ammeter connected somewhere. Okay, note the position of the pointer. Note position of pointer. So repeat for different currents. Okay. So yeah, so that's just sort of easy as that. Let's write that down. Okay. The spring constant of a different spring is 24 newtons per meter. Okay. So the spring is okay. The spring constant of a different spring is 24 newtons per meter. The spring is extended from its unstretched length by 12 centimeters. So it's extended by 12. We've got to read quite carefully. Calculate the energy transferred in extending the spring by 12 centimeters. Using an equation selected from a list of equations at the end of this paper. So let's go there then. It's a spring. So we're going to use the spring constant. Probably got used to this by now. Okay. Energy transferred in stretching. Half times spring constant times extension 12. It's half kx squared. Okay, half kx squared. But we're further along in the paper than I thought. That's fine. Scroll down. Let's see what we've gone through the other ones. Half kx squared. So let's write down the equation. Okay, so calculate the energy. Okay, so that was E. Energy equals that. Okay, if you just check back if you've forgotten, energy equals half kx. So half is a half number. K is spring constant. We're told it. We don't have to work that out. 24. X squared is extension and it's 12. 12 squared, remember. Again, no rearranging. All we have to do is put that into a calculator and we get 0.0 Okay, 0.17 joules. Okay, so something I didn't tell you there. This has got to be in meters. Okay, so this is actually got to be converted to 0.12 to get that answer. I did it on my calculator, but I didn't write it down to tell you. So that's got to be converted. It's got to be converted to meters. Let me just write a note here. You probably thought how I got the answer. Converted to meters, because that's in centimeters. Okay. Always be careful of that. Okay, so energy transferred 0.17. Okay, next question. So figure 10, this is question 6, figure 10, shows an arrangement of gears. Each gear turns around a fixed axle. Gear P, okay, gear P is turned through 1 complete revolution per second, this one. Which of the following describes the motion of gear R? 10 teeth, 10 teeth. Okay, so it actually be the same as P. They've both got 10 teeth. Okay, put the X there. Right, figure 11, okay, shows the same arrangement with gear R replaced by a rack. So a rack is just, we've got teeth on it, but it's a straight line. Okay, 10 teeth, 40 teeth. The rack can be moved up or down when the gears turn. The teeth on the rack are 2 millimeters apart. Calculate how far the rack moves when P turns through 1 complete revolution. So P is this one. Okay, so 1 complete revolution. So it's the distance equals pitch times number of teeth moved. Okay. So distance here. Okay, so it said that gears 2 millimeters apart. Okay, so it's 10 revolutions. Okay, and each is 2 millimeters apart. Okay, so you get 20 millimeters. Okay, moments. Okay, this is one people find quite a lot of trouble with. Honestly, it's not that bad. So figure 12 shows 3 toy animals hanging from a rod. So they're toys, they're not real elephants or rabbits or ducks, they're toys. The rod hangs from the ceiling by a string tied to the center of the rod. The system is in equilibrium, so it's not moving. Use the principle of moments to calculate the mass of the toy elephant. Okay, all the principle of moments is if it's in equilibrium, if the system is in equilibrium, okay, the clockwise moments equal the anti-clockwise moments. Clockwise moments equals anti-clockwise moments. Okay, that's actually the principle of moments, is if a system is in equilibrium, clockwise moments equal anti-clockwise. So clockwise moments, if you imagine the rod turning this way, that's clockwise, the way a clock goes, and that way is the anti-clockwise. Okay, so let's work out. Okay, let's work out. So first we can work out the anti-clockwise moments. So it's clockwise, and this is the other way around, anti-clockwise. Clockwise. So let's work out the moments of the duck and the rabbit. Okay. So clockwise moments is actually the elephants. Let's write the elephants on this side. So we know it's 17 away. And a moment is a mass, okay, times the distance from the pivot. Okay, we don't know its mass, so we're going to put okay, just put a big M over here, and the distance is 0.17 meters. Working meters equals 6 grams. So do did kilograms and grams. So we've got grams. I'm going to put it into kilograms. So 0.06 times, let's put this in a bracket, times, and scrub up a bit, 0.15 meters. Right, that's a rabbit. Plus then the duck. So 0.046 times the distance 10, so just 0.1. Okay, so let's put equals. So we've got so I'm just going to write all this over. So we're going to have, we keep it, we're not going to calculate it straight away. So 0.06 times 0.15 plus 0.046 times 0.1 all over, we just put that under there, 0.17. So M, okay, M equals 0.08 kilograms. Okay, if we convert that, okay, we convert that into grams, it's 8 grams. So 8 grams. Moving on. Okay, figure 13 shows a diagram of a device for use for lifting heavy loads. Piston Z, piston Y. So it looks like you push piston K down. So like piston K, you push that down. There's oils in it, and that's a metal tube. So it's like hydraulic system, that's called. So figure 13 shows a diagram of a device for lifting heavy loads. The metal tube is filled with oil. Piston Y is pushed down with a force K. This produces a force L on piston Z. Right, so yeah, this is a bit of a complicated diagram to look at. So it says piston Y is pushed down with a force K. This produces a force L on piston Z. Okay, the pressure exerted on the oil by piston Y is the same as the pressure exerted by the oil on piston Z. Explain the difference between the size of force K and the size of force L. So if you think about pressure-wise, if you exert a force of pressure on a smaller area, for a smaller force on a greater force on a smaller area, you get a greater pressure. So let's write this down, okay? Because yeah, it's quite difficult, okay, to actually explain this, obviously by talking. So let's write it down. Okay, so pressure equals force over area. Okay. So pressure equals force over area. Okay, so it's easier to write this down. So pressure equals force over area. So the area of piston Y, okay, area of piston Y is less than piston Z. Okay, therefore, less force is required to put less force is required to piston Y, okay, to gain equivalent force on piston, equivalent force on piston Z. Sorry, force on piston Z. Okay, so obviously that if you push down with this force here, because of the area is smaller, we get a greater pressure, and the oil transfers that pressure to piston Z and pushes up with a greater amount of force. Okay, so if you put pressure here is greater, okay, because it's a smaller area, and it'll push up with a bigger force. I'm just going to end the video part there, and I'll see you in the next part of the video. See you in the next part. Bye.